Hello everyone. I'm making this video on model logic because a lot of classmates were facing the same issue. So I've tried to make this video in a few parts and I've attached the timestamps below the video. So if you're facing some issue with a specific problem, make sure to jump to that timestamp. Otherwise, if you have problem with the logic itself, then cut. So I'm going to divide this video in 4 to 5 parts. The first part would be what model logic is and why do we need it. The second part would be the alpha and beta rules and the model rules, how they are derived. The next part we would like to look at the examples in the book, and the last part would be solving the problems that are there in the book. Okay, so let's just start with what model logic is. Okay, tell me why. What model logic is and why do we need it? The first thing that we need to look at is the propositional logic from our undergrad. Basically, in undergrad, we used to have propositional logic where there were two premises and we had a conclusion. What was the use of logic? Proving validity and invalidity of arguments, right? So we use model logic for the same thing, but model logic gives us a superpower. The superpower to think about possibilities. Suppose in propositional logic, I would say that M is a good man. Good people help others. Conclusion would be M would help others, right? This is an argument of propositional logic. But when I say model logic, when I come to model logic, I can think about possibilities. Now I can say that what if M is a good man? What if M is not a good man? Would then he help others? Because good men help others, right? So model logic helps us dive into these world of possibilities. Okay, and in propositional logic we had four connectives, as you can remember: if then, denoted by horseshoe; we had the disjunction, which meant or; we had the conjunction, which meant and. This was denoted as a dot in propositional logic, but here we denote it as a reverse wedge, and this was the equivalence. And negation, which was denoted like this in propositional logic, but now we denote it like this. This is the negation of model logic. In model logic, we are talking about worlds and possibilities, right? So there are two new operators in model logic called the square and the diamond. Square is known as necessity and diamond is known as possibility. Now what these two are: if I say M is necessarily a good man, then he would be a good man in all the possible worlds. Wherever, if I say diamond M, that would mean that M might be a good man, M might not be a good man, another possibility. So when we are talking about model logic, we are talking about possible worlds. So let us consider two possible worlds, world 0 and world 1. You can denote them by anything: WA, WB, world A, world B, world 1, world 2, world P, world Q, right? So consider in this possibility where there are two worlds and those two worlds are related to each other. The world 1 is accessible in world 0, and if I say square M, that M is a good man necessarily. If I'm talking about necessity, this would be the case in all possible worlds. So when I say box M, that would mean M is also true here. जब हम box की बात कर रहे हैं, जब हम necessity की बात कर रहे हैं, we are saying that वो चीज़ अगर world 0 में true है, वो हर world जो world 0 से connected है उस world में true होगी. That is what is meant by the box M. Okay, wherever if I say diamond M, which means a possibility, diamond itself means a possibility, that would mean that there exists a possibility, एक world exist करता है, world 2, in which M is the case, right? That is what is meant by diamond M. Now diamond M might not be true here. Let me denote it as diamond P. That P is a good guy. Diamond, it's possible that P is a good guy. Then in a possibility it would be true, right? If I say diamond P, if diamond is possible somewhere, then it would be possible in another world, W2, But P might not be possible here, and I might write not P here. P might not be a good guy in possibility 1, right? But M would be true here also, because M is a necessary case. It's a necessary case. This is how we denote necessity and possibility in modal logic. The next thing that we'll need to look at are the alpha and beta rules. Now, these are not called alpha and beta rules in logic as such. These are known as the rules for operators. Because see, when we are talking about model logic, we are using the truth tree method or the tableau method. हम जो method use कर रहे हैं उनका नाम है truth tree method या tableau method. What do we do in that? When we need to find out the invalidity or validity of an argument, we make truth trees which look like this. There are truth trees, right? There are branches, there are stackings. Whenever there is a branch, we call it the branch. Whenever things are stacked in one on top of the other, we call it stacking, right? So you can see the alpha rule of implication is the branched rule, whereas the beta rule of implication, the if and then, is a stacking rule. Okay, so when we are following this truth tree method to find out the invalidity and validity of arguments, we need to follow some rules. Okay, and these are called the truth tree rules or the logical rules for operators. Okay, for the operators, implication, conjunction, disjunction, or equivalence. So how are these rules formed? We'll also look at that, so that it is easier for you to remember them. First thing, and just in case if you forget them in the test or the exam, you can just on that spot look at it and figure out what it is supposed to. तो हम इस डेरिवेशन पे ध्यान इसलिए दे रहे हैं ताकि अगर आप एग्जाम में भूल जाएं तो यू कैन जस्ट लुक एट इट एंड फिगर आउट व्हाट विल बी द केस, व्हाट would the rule say. Now you can see here that alpha rules are for the operators where we don't have a negation in front of them, and beta rules, as we are calling them beta rules, they have a negation in front of them. Now we'll look at how these are derived and what's their function. So let's begin with the alpha rule of implication, or A horseshoe B. When A horseshoe B is the case, the alpha rule says that either not A or B. To understand how it is derived, we would look at the truth table of A implies B. So we're looking at how the alpha rule of implication is derived, looking at the truth table: true, true, false, false, true, false, true, false, and the operator value of implication: true, false, true, true. You can see the only case where the truth table instance is a false is when A is true but B is false. In the other three cases, it's true, right? So when we are looking at the alpha rule, the instance where A implication B is right, there are three possibilities. Either when A is true, B also needs to be true, or when A is false, then this implicative function is true anyway. It does not matter if A, B is true or false. If A is false, this is going to be true, right? This is what we represent here, that when A is false, like in these two cases, this thing A implication B will be true anyway, and if A is true, then B will also have to be true. So there are two possibilities, right? A branching rule. Similarly, for or, the conjunction, we can say that when A or B is true, which is true in all the cases until both of them are false, right? This would imply that this thing holds true in all the cases where either A is true or B is true. See, where either A is true, it is also true. When B is true, this is also true, right? This is like saying A or B. Either A comes to the class or B comes to the class, right? We can also say that if A is coming to class, the sentence that either A or B comes to the class is true. And when B also comes to the class, the sentence either A or B comes to the class is true. That is how you understand it from natural language. So this is how you get the branching rule, the branching alpha rule of conjunction or or. Similarly, when you look at the beta rules, they are just the opposite of alpha rules, right? When we are looking at the beta rule of implication, we are looking at the only instance when the A implication B is false. It's this instance, right? And it is false only when the A is true and B is false, right? And there's no possibility A needs to be false, sorry, A needs to be true and B needs to be false. Only then this implicative function A implies B would be false. This is what we are writing in the beta rule, that when A is true and B is false, this would be the case, right? Or when this would be the case, this would imply that A is true and B is false. So A implication B is false when A is true and B is false. That's why we have written it in a stacking manner. Similarly, with the disjunctive function, when A or B is false, then both A and B need to be false. If I say that either A or B came to the class is false, that would mean that A also did not come to the class and B also did not come to the class. That is how you understand it from natural language. We have just written it as not A and not B, right? Because of this, the only case where A or B was coming false when both A and B were false. So that's why we have written it in a stacking manner. Similarly, moving on to the conjunctive function, we can say when A and B is true, both A and B need to be true. If I say that both A and B came to the class, then A also needs to come to the class and B also needs to come to the class. Similarly, when you look at the truth table, you can see that it is true only in the case when both A and B are true. So that's why we have written them in a stacking manner, A and B. Whereas in the beta rule of conjunction, where A and B is not the case, we can write that A is also not true or B is not true, right? Because when either one of them is false, the result is false. When B is false, it's also false. When A is false, it's also false. So both of them need, if either of them is false, the implicative function A and B would be a false function, right? You can see it from the truth table. So it's like saying that it is not the case that A and B both came to the class, right? So if A not comes to the class, that would also mean that it is not the case that both A and B came to the class, and when B also not comes to the class, this would mean that both A and B came to the class is not true, right? So either of the two would negate it, right? Similarly, for equivalence, the definition of equivalence says that when A is the case, B is also the case, and when A is not the case, then B is not the case. And the negative rule or the beta rule is exactly opposite of this. When A is the case, then B is not the case, and when A is not the case, B is the case. So beta rule of and alpha rule of equivalence are fairly easier to remember. This is the alpha rule and beta rule that we are going to use in the truth tree method when we are trying to figure out the validity or invalidity of the argument. So now let us talk about the modal operator rules, because now since we are dealing with two new operators called the modal operators box, which means necessity, and diamond, which means possibility, there are four more rules that we need to work with while solving for validity and invalidity of arguments through truth tree method, right? So the first rule, shortly called M1, is written as not box A in world I. This I is nothing but an imaginary world, right? The world that we are talking about, because I told you that in modal logic we are always talking about possible worlds, right? We are referring to specific worlds, world 0, world I, world A, world P. You can call it anything. So let's just say that not box A is the case in world I. Then we can write that diamond not A is the case in world I also. Now what is meant by this? We can try to understand them by natural language, by using natural language. See, saying that not the case that box A in world I, okay, that's like saying that this pen is necessarily not black, right? Necessarily not black, because I said that this pen is necessarily black, and that is not the case in world I. By writing a negation in front of it, this can prove to be a little complicated, but then once you think about it, it's intuitive also, right? When I say that this pen is necessarily not black, right? When I say that this pen is necessarily black, box A, that is not the case. That means this pen is necessarily not black. This also entails that there is a possibility of this pen not being black, right? Diamond not A. Diamond means there is a possibility of this pen being not black, right? Not A. So if A denotes the pen being black, and I say that it is not the case that this pen is necessarily black, that just means that there is a possibility of this pen not being black. That necessity entails a possibility. If something is necessary, there is also a possibility of that thing happening, right? That is nothing but the rule M1. Similarly, for rule M2, when I say that it is not the case diamond A in world I can write it as box not A in world I. What would that mean? Let's think about it. That would mean if this pen is possibly black, diamond A is not the case. Negation diamond A, then that would imply definitely, necessarily, box not A. What I mean to say is, if there's no possibility of this pen being black, then this pen is necessarily not black, right? If there's not even a possibility of this pen being black, this would necessarily not be black in the same world I, right? That is what we say when we write not the possibility A would imply necessarily not A, right? Now let us look at the rule M4 before rule M3. Rule M4 says if there exists a possibility A, diamond A in world I, that gives us the power to open a new world, say IRJ. This gives a power to make this world I accessible to world J. Or I should rather say, this gives us the power to make this world J accessible to world I by writing IRJ. When we solve for questions, we often write 0R1, 0R2, 2R3. Why are we writing this? We are making these words accessible to these worlds. We are opening these new worlds, world 1, world 2, world 3, right? So the definition of diamond is possibility, right? And that possibility will hold true in some possible world. So this rule M4 is nothing but that only. That when I write diamond A, I'm opening or making a possible world J, imagining a possible world J which is related to world I. In that world, A will be true, because A is a possibility, and that possibility will hold true only in a possible world, and that possible world is nothing but the world J, right? So I can write diamond A as A at J, but in a possible world J that I have opened. What is important is the position of this arrow. When we have diamond, we can make this arrow and write IRJ and A at J. Whereas if you see in rule M3, the world is already existing, and then only we can go from box A to A in that world, right? How? When I say that box A is the case in world I, and that world is necessarily related to a world J. This is already the case. The world 0 is already related to world 1. Then I can say if that box A is the case in this world, A will also be the case in world 1. Right? This is what we mean by rule M3. That if box A is the case in world I and there exists a world J which is related to world I or which is accessible in world I can write that A would be the case in world J. This is nothing but rule M3. So this is how we can understand these model rules with the help of natural language. So these are the model operator rules for truth tree method. If you have any doubt, let me know in the comment section so that I can reach out to you better. Okay. Let us now move on to discuss the examples in the book. So let us now move forward to the final section of this video. In the next video, we will try to solve all the questions from the exercises, right? So if you have a doubt in specific questions from the exercise, you can directly move on to the next video. But in this video, let's just look at this example from the book. Before moving on, I would like to remind you that in propositional logic, we used to find the validity of invalidity of an argument through a method called as short truth table method or the invalid truth table method, where we used to assume that this conclusion is invalid and then look for contradiction, because in a valid argument, if the premises are true, conclusion is supposed to be true, right? In a valid argument, if the premises are true, the conclusion should be true. The argument would be invalid if the premises are true and the conclusion is false. So we used to assume that the conclusion is false and then make truth tables and look for contradictions. If we found the contradiction, that meant that our assumption was wrong and the argument is a valid argument. If we did not find any contradiction, that meant that our assumption was right and the argument is indeed invalid. So we are going to do the same thing here. So we are going to proceed with the same thing. We are going to assume that this conclusion is invalid. So this is the sign of logical implication. This means that whatever comes after this is the conclusion, first thing, and that the argument is a valid argument. If we have this sign, that means that the thing is not logically implied and that the argument is invalid. So our first step was negating the conclusion. Let's do that. Let me just write these premises as the first step. Okay, and then Our real first step is then negating this conclusion. So right, negation of box A implies C at 0. I have mentioned 0 after here because in model logic, as I told you, we're always talking about worlds, right? We're always talking about world 1, world 2. So this is the case in world 0. We start with 0 so that we can naturally proceed to 1, 2 and 3. There's no problem if you start with world 1 and then proceed to world 2 and 3, but then that's just the case. You start with world 0. That's the natural practice. So the first step was writing the premises, second step was negating the conclusion, the third step is applying the alpha rule of conjunction on the first step. So by applying alpha rule of conjunction, I write this and this, the third and fourth step, right? Because alpha rule of conjunction said that A and B can be written as A, B in a stacking manner, and this whole thing, box A implies B, is our A here, and this whole thing, box B implies C, is our B here. So I can write 3 and 4 as box A implies B at 0 and 4 B implies C at 0. The next step, fifth, can be written by applying the rule M1 on second. Okay, so second was negation of box A implies C. But when I apply the rule M1, I can write negation box as diamond negation. So a quicker way to remember this is whenever there is negation in front of the box, I can write it as diamond negation A, and whenever there's a negation in front of diamond, I can write it as box negation A. So the fifth step was applying the rule M1 on 2, and then since I got a diamond, wherever I get a diamond, I have to open a new world. If I get 2 diamonds, that means I will have to open 2 worlds. So when I got a diamond, I opened the world 0R1, and then I wrote that was the case in the open world 1 using the rule M4. Now since I have this, I can again imply the beta rule of implication, because there is a negation here and the main operator is implication. By applying the beta rule of implication, I get this 8th and 9th step, and then the 10th step would be using these boxes again. 3 and 4, in the step 3 and 4 we had boxes. We will again use those boxes with the already open world 0R1, and by applying the rule M3 on 3 and 4 we get this. Okay, now after this we again apply the alpha rule of implication on 10th, so we get this, and then again we apply the alpha rule of implication on 11th, so we get this. This is nothing but applying the rules. And then finally, since we find contradictions here, this line says that A is not the case in world 1, and this line says that A is the case at world 1. I can write that this is contradictory. After opening these branches again, I can say that not B is the case in world 1 and B is the case in world 1 is also contradictory, and C is the case at world 1 and not C is the case at world 1 is again contradictory, so this branch is also closed. Now see, the basic method how we are proceeding here is, this is my understanding of the subject, that first we need to simplify. Okay, first we need to simplify the argument that has been given to us, remove all the negation in front of the boxes, all the negations in front of the diamonds, and then once we reach to only diamonds and boxes, like these propositions, only boxes here and only diamond here, then wherever there is a diamond, we need to use these diamonds to open new worlds. Okay, then we use the diamonds to open new world, and the third step is, after solving those diamond propositions with new worlds opened, we have to use boxes with already opened worlds, the worlds that we already opened with diamonds. So this is how you proceed. First you simplify everything, you remove the negations, then when you are left with negations and boxes and diamonds, you use the diamonds to open new worlds, and then use the boxes that we already had with the worlds we have now opened to further simplify them, and then just keep applying the operator rules. Finally you'll get contradictions in all the branches. If you have the sign of logical implication and you are not getting contradiction, that means you are doing something wrong. Wherever if you have a sign of not logical implication and you are getting all the branches contradicted, that is also wrong. That means they are doing something wrong. So in the next video we'll be solving all the questions from the exercises. So if you have any doubts in the exercises, do watch that video, and if this is still unclear to you, please again watch the next video, since we'll step by step move forward and find out how and where we need to apply these rules. Thank you so much.